The next concept we're going to talk about is called the intertwiner, and also this is related to this concept of unitary equivalence. So roughly speaking, I want to say when our two representations are basically the same, okay? What do I mean by the same is that we can find some kind of unitary that kind of implement these transfer kind of one to the other, okay? So first of all, let's give this definition of an intertwiner. So if you have a two unitary representation, let's call them pi1, pi2. They may represent your group G on different spaces, let's say H1, H2. Then a map, let's call it T, from H1 to H2 is called an intertwiner. If what happens is you apply pi1 first and then you transfer it to T, or you do the T first and you transfer by pi2, then you end up with the same thing. So one way to think about it is this picture. So you have your H1, the T maps H1 to H2, and your pi1 is basically a map from H1 to H1, and pi2 is a map from H2 to H2. And of course, you can do this by T as well. So if this diagram commutes, meaning if you go either way, so you go the way from the top or from the bottom, you end up with the same vector, then these two are basically these two operators are the same, and we call this T an intertwiner, okay? So let's denote the set of intertwiners. So let's let C of pi1 to pi2 be the set of intertwiners. And so just in the special case, if I have pi1 is equal to pi2, then let's call it C of pi, okay? So if, let's say, pi1 is equal to pi2 is equal to pi, then sometimes I just use C of pi to denote C of pi from pi to pi, okay? You didn't intertwine of pi to itself, okay? And if you have a unitary operator, so if one of these intertwiner is a unitary, then we say these two representations are unitary equivalent. So here's the definition. So we say, pi1 and pi2. So let's do pi1 is unitarily equivalent to pi2 if there's a unitary operator U, a unitary, and U is inside C of pi1 and pi2, okay? So here the unitary is a unitary from, so U is from the bounded operator from H1 to H2. So that being a unitary, well, you can say preserve the inner product. So the inner product on H1 will be the same as the inner product you apply to U, and then you take the inner product in H2. Another way is saying the U star and U star U, they're both the identity, one on H1 and one on the H2, okay? So you can define a unitary operator this way. But if you have a unitary operator, then if you look at the formula we had, so this formula, so what you end up with is you apply pi1 and then you apply U. It's the same as you apply pi2 of x and you apply U. But then because U is a unitary, so you can take its inverse or its adjoint. So what you end up with is like these pi2 of x is just going to be equal to U times pi1 of x, and you take the adjoint, say U star, which is equal to U inverse. Okay, so then you have this kind of formula. So pi2 is kind of the pi1 conjugate by a unitary, okay? So just notation-wise, so we write, let's just use this convention, pi1 is unitarily equivalent. Let's just use this notation. All right, so now we have basically when they're both unitary, it just means pi1, pi2, they really look like the same representation, okay? You're implemented by some unitary. And let's think about what's the special case about when pi1 and pi2 are the same, okay? So if you look at what's C of pi, so this is essentially all the operators T inside the bounded linear operator on the H of pi, so that you have a T kind of commute with your pi of x, okay? So this is T of pi x equals to pi x of T. And if you think closely, well, this is essentially all the t that commutes with all the x. So this is for all x inside G. So you can think about this is as the commutant of the pi x. Okay, so x is inside G, and you take its commutant. Okay, so this is the commutant. Okay, essentially every operator that commute with all these pi x. Okay, or sometimes you just write pi of G, the first commutant. And this is something in the operator algebra. I don't want to talk too much about it, but whenever you're taking the commutant, then you always have something that's weak operator star closed. Okay, so in particular, this is going to be weak operator closed. Okay, so that's kind of some standard result from operator theory. If you move on to take, say, pure math 810, the operator algebra, you'll sure study these kind of stuff. All right, so we have the C of pi is operator closed. And moreover than that, if I have a t inside C of pi, then what I have is that if I consider t star, okay, and I evaluate t of multiply by pi of x, then you can think about this t star of pi of the x inverse, the whole thing star. Okay, so you can think about this pi x is pi x star star, and then you do the star representation, you move one star inside, and this is essentially just pi of x inverse times t the whole thing star. But then because t and pi, they commute, so you can move the t to the other side. You have t of x inverse this whole thing star. So you end up with pi x and t star. So in other words, your t star also commute with your pi. So this implies your t star is also inside C of pi. All right, so because of that, well, you can see that, well, C of pi clearly is also a linear space. So if you take linear combination, you still get in there. And moreover, if you take any the product, so if you have S and T inside C of pi, then their product is certainly inside C of pi. So what do I mean by that? Essentially, what we prove that C of pi has some kind of a star algebra structure. So the algebra meaning you have linear space and you can multiply them. And the star means once you take the adjoint, it's still in there. And it's also a WT closed star algebra. So this is essentially what we call the Norman algebra. So this is a the Norman algebra. So the C of pi, the intertwiner of pi to itself, is always a Norman algebra. And the Norman algebra, they are quite special. Okay, so if you the properties will be studied in the next course, let's say pure math 810 at Waterloo. But let me just use some of these von Neumann algebra property to prove the following lemma. So this is called the Schur's lemma, or let's just write lemma. So pi is actually irreducible, can be characterized using the C of pi. Okay, so if the C of pi is given by the constant times the identity. Okay, if and only if the commutator for pi to itself is always multiples of identity. Clearly, these multiples of identity has to be in C of pi. Okay, but the harder direction is showing that these two are actually equivalent. All right, so let's prove this fact. So first of all, if your pi is not reducible, so if pi is reducible, so there exists a, let's say, H0 is an invariant subspace, and you have these H0 is not equal to the 0 and is not equal to H of pi, so some non-trivial invariant space. So if you let the P to be the orthogonal projection, so orthogonal projection onto this H0, then what happens is that if you think about P with pi of x, they have to commute. So why is that? Well, the idea is fairly simple. I usually like to write it using this operator matrix representation. So if you think about this H of this pi, you decompose using this H0 to its perp. So what it's saying is that this pi has something in here and something in here, but 0 on the off diagonal. And what is the orthogonal projection? Well, the orthogonal projection onto H0, if you write like that, well, what you end up with is that, well, you map H0, a vector in H0 to itself. So this is essentially the identity on here. And it will kill off everything else. So you get 0 over there. And just from this representation, if you do the matrix 2 by 2 matrix multiplication, then you end up with pi x times p and p times pi x. They have to be the same. Okay, essentially it will just leave the left upper left corner. Okay, so this is essentially just this upper left corner. You kill off everything else, and you have these pi here. Okay. All right, so they clearly commute. So you have this P is now inside C of pi, and this P, because the H0 is a non-trivial invariant subspace, it's not equal to 0 and it's not equal to the identity. So it has to be something that's non-trivial. So the C of pi is containing something that's not multiple of the identity. Okay, you finish one direction. And for the other direction, so if if you can find some operator, let's say A is not equal to C times the identity, maybe let's call it A0 here. Then what you can do is first of all, you can find some self-adjoint operator that's not equals to the identity. So let's say A is equals to half of A0 plus the A0 conjugate. That's also inside C of pi. I should say A0 is inside C of pi. Because you have a star linear algebra structure on C of pi, you have these kind of self-adjoint operator. And so this A is actually a self-adjoint operator, okay? So because you have these kind of self-adjoint operator, and if you look at its spectrum, I didn't really talk about spectrum in this course, you learn it in the operator theory or A10. So this spectrum is not just the identity, okay? The spectrum has something else in there because you're just taking A and A conjugate. All right, so what you have is that if you take the von Neumann algebra generated by this A0, so basically the smallest weak operator closed star algebra, that's going to be the von Neumann algebra generated by this A, not A0. Then what you have that is that because your C of pi is also a von Neumann algebra, that's going to be inside the C of pi, okay? But inside of a Neumann algebra, what you have is that you have this thing called a L infinity function calculus, essentially meaning you can apply any L infinity function to your self-adjoint operator, and you get something again inside of a Neumann algebra. So in other words, let me just say briefly, if you have some Borel function on the spectrum of this A, then you apply this Borel function and you get something that's still contained in is the Neumann algebra. And of course, because your spectrum is not just the one, then because your A is not just the constant identity, then you can always pick some subset. Okay, so you can pick some subset E, which is of course not the empty and is not the spectrum, the entire spectrum, so that this E is Borel. And if you consider the characteristic function on this A, this is going to be inside the Neumann algebra generated by your A, which is inside the C of pi. But this one, because you have an L infinity function, so this if you call it P, then the P square, which is equals to chi E square, evaluate A, but since you have a characteristic function, this is just chi E of A, so this is still equals to P, so that's a projection, okay? And this P, because this chi E, the E is not the empty and it's nor the entire space, you have this P is not equal to 0 and not equal to the identity, so you have some orthogonal projection, okay? So this P is an orthogonal projection inside the C of pi. And if you just let H0 to be the range, okay, the PH, okay, close it if you like. Okay, if you do the projection, then this is going to be an invariant subspace. Okay, it's invariant for this pi. The reason being is that if you think about what happens when you do the P of pi x equals to the pi x times P, if you just follow what we have, this P is essentially a orthogonal projection to its range, so it looks like the identity operator on H0 and 0 everywhere else. And your pi, you can divide it into these based on these decomposition. So you have H0 direct sum H0 perp, and then H0 direct sum H0 perp. So on one hand, you have a P times pi x. You multiply your this identity with your pi, so you have a bunch of stuff like that. Okay. So what you end up with is that you only preserve the top two thing, but on the second row, they're all becoming 0. Okay. And if you do the other way, if you do pi x times p, which is you do your pi first, and then you multiply this identity and a bunch of 0, then what you end up with is that you only have the first column. Okay, so the second column becomes 0. And just comparing that, these two, you see that these off-diagonal corner has to be 0. So that's why this pi has this H0 as invariant subspace. Okay. So this finishes the proof. So basically your pi has to be, pi is reducible, okay, reducible. Okay, so of course here we use some theory about the Norman algebra. If you're not familiar with that, you can pick up some book, or you can just take the operator theory, the operator algebra course, all right? Okay, so as an immediate corollary, we have the following nice lemma. This is sometimes also called the Schur's lemma. So it's essentially telling you the following. So if you have two irreducible representation, let's say pi 1 and pi 2, they're irreducible, then there are two things can happen, okay? So then either you have that they are not unitary equivalent, okay? Either the pi 1 and pi 2 are not unitary equivalent. And in this case, their intertwiner is actually just equals to 0. Okay, so pi 1 and pi 2, nothing except 0 can intertwine them. Or if they are unitarily equivalent, so pi 1 and pi 2 are unitarily equivalent, in this case, the C of pi 1 and pi 2, they're just going to be a one-dimensional space. Okay, so it's one-dimensional. Okay, so it's essentially meaning you can only find one unitary that kind of implement this unitary equivalence. Okay, you can take the span of that one unitary, they're still going to intertwine them, but that's pretty much it. Okay, so the proof is kind of simple from what we just proved. So if you have a t inside the C of pi 1 and pi 2, then automatically you have the t star is going to be inside C of pi 2 with pi 1. Okay, kind of easy proof. So what you can do is that, well, now if you apply t and you apply t star first and then you apply t, so this will transfer you from pi 2 or h2 to h1 and then back to h2. So this one is going to intertwine the pi 2 with pi 2, so it's inside C of pi 2. And similarly, if you do the t first and then t star, that's going to transfer you from pi 1 to pi 1, okay? Well, so in other words, what do you have that because your pi 1 and pi 2, they are irreducible representations, so automatically you have this tt star is either going to be multiple of the identity or they're going to be 0, okay? Well, if they're equal to 0, of course, they are not going to be unitarily equivalent, okay? So let's just consider the case when they're not equal to 0. So if you can find some t so that this tt star is equal to c times the identity where c is non-zero, okay? Well, then what happens is that you can, well, then the t star t, by just looking at the operator norm, you can say that this is also the c times identity. Well, this is, the first one is the identity on H2, the second one is the identity on H1, but they have to be always equals the identity. So if you let the u to be the c times negative half to this t, this is going to be a unitary operator, and because you're only taking a scalar of that, that's going to be sitting inside C of pi 1 to pi 2, and the u is unitary, okay? Just because you take u star and u star u, they're both equal to the identity, okay? So of course, in the second case, they're both you now find a unitary, so they're going to be unitarily equivalent. Okay, so in this case, we have pi1 is unitarily equivalent to pi2. So now if we want to see that this intertwiner space from pi1 to pi2 is one-dimensional, so let's take any other operator, let's say t prime is inside the C of pi1 and pi2. And by basically the same argument, we know this t prime is a multiple of the unitary, so you can renormalize it. So let's just assume that is another unitary. So if you consider this t prime, if you multiply the inverse of this unitary times the unitary, this u we just found, then this is going to be inside the C of pi1. Well, start from pi1 and then you end up in pi1. So it's an intertwiner for the pi1. But we know this is multiples the identity. Okay, so in other words, this t prime inverse times u is going to be inverse times u is going to be c times the identity. In other words, all other unitary, this t prime, is going to be equals to some unitary, some multiple of this unitary. Okay, so this c prime is just 1 over c, which is going to be a constant scalar. So in other words, your the space C of pi1 to pi2 is going to be one-dimensional. Okay, so let's finish the proof. So as a quick corollary, so what happens when we talk about unitary representations of abelian groups? So if you have a G that's abelian, then every unitary representation is going to be a character. Okay, you can think about it as a representation on the one-dimensional space. Okay, so every irreducible representation pi from G to B of H pi, this will have this H pi is one-dimensional. Okay, dimension of H1, H pi is equal to 1. Okay, because it's irreducible. So essentially, this corollary is basically going to say that the analog of the unitary representation in abelian groups is essentially just the character group. Okay, so let's prove this fact. Well, that's fairly simple once we have all the Schur's lemma. So because your G is abelian, if you think about what happens to this range pi of G, so pi of G is going to commute with all the pi x, okay, all the pi x. So in other words, all of these pi of x or pi of G, that's going to be contained in this C of pi, okay? So it commutes with all the pi. But because your pi is irreducible, so while that just implies your C of pi, we just saw is a multiple of the identity, and because again is irreducible, so the space you can just reduce it to the one-dimensional ones. Okay, so each of these pi x essentially just equal to cx times the identity, or you can think about this pi s from G to the cx. Okay, so pi is essentially just x maps to cx, so you can treat this h pi as a one-dimensional space. Okay, so in other words, let me just do the quick remark as we already noticed. So the unitary representations of a locally compact abelian groups, that's just equals to a Steele group. Okay, so because you need to be unitary on the one-dimensional space, each of these number has to be on the unit circle. So this is essentially the dual group. So for non-abelian groups, the dual group, as we see, is usually very small. So the idea behind all these is that the unitary representation is going to replace the role of the dual group for these analysis on the non-abelian groups.